CPU250 with variable frequency drives. It's roughly about 20 minutes, give or take. But if you have any questions, feel free to put them in.
Hello and welcome to today's webinar. Today we will look at using the Micro CPU250 with variable frequency drives. Let's take a look at our agenda for today. We are going to start with a quick review of the CPU250 and then we will dive into variable frequency drives. We will talk about interfacing with those drives through I/O signals and through networks like Modbus RTU, and there will be demonstrations throughout, and we will finish with a Q&A session. The new CPU250 is one of our new modular controllers that are part of the Micro series that are great for simple and smart applications. They do a lot more than just simple applications, but to date, the Micro series has consisted strictly of all-in-one controllers or controllers that include a display. CPU200 and the CPU250 shown on the screen at the right, those do not include a display. And today we are going to be talking about the CPU250. The CPU250 is fully featured. It has got all kinds of interfaces on it. It has a full array of I/O type connections internally built in, and it also has connectivity like Ethernet and CAN and serial ports. It has the ability not only to have built-in I/O but also to add modular I/O to the side of the unit using standard OCS I/O module snapped into the side, and from the field bus standpoint and industrial Ethernet standpoint, it has a lot of connectivity. Now on the connectivity side, today we're going to be talking about Modbus RTU, which is a great protocol to use for VFD control. Now let's go into built-in I/O for the CPU250. Now one of the highlights of the CPU250 from an I/O standpoint is the fact that it has 34 built-in I/O points. That means it can take care of a lot of applications, and one of the highlights are the flexible inputs, which are 8 inputs that can be either digital or analog. So if you have a heavy analog application, you have plenty of analog inputs. If you have a heavy digital application, you have plenty of digital inputs. So lots of flexibility in the built-in I/O of the CPU250. And today we are going to highlight the I/O signals that allow us to use VFD control using I/O. Now we're going to dive into variable frequency drive. What is a variable frequency drive? It is an intelligent electronical component that is designed to control an AC motor. VFDs change the frequency and the voltage of the AC that they send to the motor, which allows VFD to control the motor speed. Now, how does a VFD work? It converts the AC that is connected to it to DC and then back again to the variable frequency AC that is sent to the motor. And VFDs are everywhere, just like PLCs. Let's start by talking about how VFDs and PLCs are used together. First of all, there is no requirements that you have to use a PLC to control VFD. They can work standalone and they are often used that way. However, it is very common for drives to be controlled by PLCs, so you get a good coordinated machine control. A most common method of controlling VFD from a PLC, there are two of them. First would be to use I/O signals to start and stop the motor. Those are digital and analog signals that every PLC includes. That is just one method. The other method is to use a network and send those same commands digitally instead of through an I/O signal. Now let's start looking at the common control connections if you're going to use I/O from a PLC to control a drive. Now there are lots of different I/O that could be used. This is probably a basic common type approach. First of all, from the PLC, you are going to have a digital signal that is a run-stop command to start and stop the motor. They will probably be forward-reverse command in a lot of applications, and they will definitely be a speed reference of some sort. And using it is an analog output, and usually it is an analog output from a PLC to the drive that is scaled to frequency. So a minimum analog signal to the drive from PLC will give you minimum frequency for the motor, and a maximum analog signal will give you maximum frequency for the motor. So that is the signals that are most typically going from the PLC to the drive. Now coming back the other direction, you are going to have a digital signal that tells you run status, so the PLC knows if the motor is turning or not, and there will be some sort of feedback, usually another analog signal coming into the PLC this time that is scaled for frequency, so the PLC knows that the drive is running at. That tells them the speed of the motor. So again, there are lots of different variations, but This is the most common setup. Now what if we're talking about using network connections between PLC and the drive instead? Well, there are many choices available. You have got Modbus, both serial as well as internet. You have got Profinet and Ethernet IP, which are everywhere. You have got CAN Open, and even though all these networks are available in most drives, usually it is Modbus RTU or Modbus over RS45 is the one that is the most commonly available, built into the drive as a standard. Usually those other protocols or options that have been added to the drive, whereas usually Modbus RTU is built in. Now let's talk about CPU250 and its interfaces that it supports for controlling a drive. From a network standpoint, it supports Modbus both RTU and Modbus TCP, Modbus over Ethernet, and supports CAN Open. So both of these options that are built into CPU 250 if you want to control using a network. If you want to control using digital or analog I/O, as we mentioned earlier, the CPU 250 has a huge amount of built-in I/O and can easily control the drive that way, so you have got options. Now which should you use? Should you use the I/O approach or should you use the network approach? Let's talk about the advantages of each. Let's start with the I/O. What are the advantages of using I/O to control FVD? It works with any drive. All drives are going to have the ability to be controlled via I/O signals. Why is that important? The advantage of using I/O is that if they ever have to swap out the drive, they cannot get an exact match for the drive that was originally put in the system. They have a lot of choices of drive replacement. In other words, they can put any drive in there and control it using I/O, and they do not have to do any reprogramming or anything else. So those are the advantages of using I/O. But networks have an advantage as well. First of all, if you are using I/O signals to control the drive, you can use I/O signals for other purposes to control other components. So that is an advantage that can save costs in a lot of cases. When you are connected over a network, you have the option of receiving detailed diagnostics from the drive. So not only that the drive is faulted, what the fault codes are, for instance. So that is an extra information that can be valuable. So which should you choose? First of all, there are no wrong answers. Both approaches are valid and you can choose either approach. Now for today's demo, we are going to use both. We are going to use I/O signals to control the drive in our demonstration today, and we are going to use Modbus RTU as diagnostics for the diagnostics purposes. Therefore, we have the advantages of the diagnostics from a Modbus standpoint, and we have the advantage of being easily able to swap out the drive by using the I/O signals instead. So let's start with the specifics and what we need to do with Modbus connection. First of all, Modbus RTU is uniform. It has a twisted pair plus additional conductor that is needed for RS45 communications. So the twisted pair is going to carry the communications data, and then the extra conductor is going to carry common to avoid any kind of common mode ground issues between the two components. So all three wires are important. The communication signal needs to be over the twisted pair, and the extra conductor is where you put the common, and the extra conductor can be half of an unused or otherwise unused twisted pair. Now termination needs to be done at both physical ends of the network. On the drive side, many sides have a switch you can throw or some other methods of adding termination on the end. In the case of our example here, with the control techniques drive, we physically added 120 ohm resistors to the end of the network. Now on the CPU 250 side, we could have added a physical resistor on the end of the network, but that could be difficult using a modular DAC sometimes. But the CPU 250 does have a way of adding termination simply by turning on a system bit. There on the screen, we are showing you that SR152.1, when turned on, will add termination to MJ2 port, which is the RS45 port. So that can be easily done in your logic. Now from a Modbus reference standpoint or Modbus address standpoint, since we are using Modbus strictly for diagnostics, in our example today we have chosen a series of Modbus addresses in the M400 drive that allow us to monitor voltage and power RPM, a signal that tells us if the drive is healthy or not. and if it is not, we have the ability of reading trip codes, not only what the trip codes are, but when they occurred. So that is the specific diagnostics we are going to be using today in our demonstration. You could have chosen completely different references, and if you are using other drives, you are going to have different Modbus addresses. Now let's talk about I/O connection between two devices. So first of all, there is a digital output that we have wired in our demo to Q1 on the CPU250 that is going to tell the drive to run. Then the drive is going to feed back a signal into input 1 on our demo for the CPU250 that tells the CPU250 that the motor is at rest. Then we have got an analog output coming from the CPU250 to the drive. That is the speed reference. It has 0 to 10 volt signal in this case, and it is scaled to a frequency or motor speed at a minimum analog value of 0 volts. We are going to get the minimum frequency out of the drive at the maximum analog voltage of 10 volts. The drive is going to cause the motor to run at maximum frequency. So that is the speed reference for the CPU250 to the drive. And then we have got feedback coming back to the other direction. Another 0 to 10 volt analog signal scaled to frequency. So the CPU250 knows the speed that the motor is turning as a verification. And then we also have a 24 volt and 0 volt connection between two components. And again, for the control techniques drive that we used in the demonstration, we have got the terminal numbers listed there as well. Now in the upper right hand corner, we are showing the addresses for that specific I/O points are mapped to in our demo program. And you will notice that everything's straightforward, with the V1 terminal, which is the first analog output, that is the voltage analog output that is mapped to AQ5. And then the first flexible input, which is terminal I9, when it is configured as an analog, that is mapped to %AI1. So just to make clear what the I/O references are, we are showing them there on the screen. For our demonstration, let's go ahead and start on the bench. Let's take a look at what we have got here. So we have got our CPU250, and to the left over here is where we have our motor and drive. We have chosen to do a hybrid approach with this demonstration of interfacing the CPU250 to the drive. So with hybrid approach, we use both I/O points to interface to the drive as well as Modbus. Why do we do this? Well, we get the best of both options, so we have the ability to control any drive through I/O. One analog in, one analog out, one digital in and one digital out, and we get the benefit of the diagnostics over Modbus. So if we ever have to quickly swap out the drive, we can do so, and we can basically swap it out any drive that we can control via I/O, which is almost every one of them. And we also get the benefit while we have our original drive or any replacement drive of the same type, that we can easily get lots of diagnostic information over Modbus. In terms of what we have got wired, we have one analog output here, which is providing the same speed reference for the drive. We have an analog input that is wired here through one of the flexible inputs that is providing feedback on actual speed for the drive. And then we have a signal output going to the drive as a run signal, and a single input coming back telling us that the drive is at rest, that we are not moving. That is how the signal is set up. The drive is not moving. And then we have also got common and 24 volt connected as well here. And here is our RJ45 talking to Modbus RTU. So let's go take a look at Seascape side of things. Let's get started through the hardware configuration, and because we are primarily controlling the system using I/O, let's take a look at our local I/O. Now there is nothing going on in the single digital input and output that we are using here with the drive. These are all just defaults, so we are not going to go through that. And then we just have one analog input, which is configured as a flexible input, and one analog output. So let's take a quick look at those. Now for this particular drive, we have chosen to use 0 to 10 volts on the input side, as well as 0 to 32,000 on the range. So at 10 volts, we are going to have 32,000 counts. At 0 volts, we are going to have 0 counts. As we mentioned before, this is providing the feedback from the drive, telling us the speed that the motor is turning at. So that is one analog input. The rest of them we could configure however else we needed in our system. On the analog output side, remember these are not fully configurable, so if you are going to use voltage, we have to use one of the second group of the 4 analog outputs. So we are going to use the first of the voltage analog outputs, which happens to be analog outputs number 5. Connect to the V1 terminal, and again, scaling is the same, 0 to 10 volts, 0 to 32,000, and this is providing the speed reference. So when we are sending 10 volts to the drive, we have done that by pushing 32,000 in the register, which is AQ5, and that should cause maximum speed for the drive. So that is what we have got going in the I/O configuration. We do not have a lot of logic in here for controlling those 4 I/O points or monitoring those 4 I/O points. You can add those yourself with a particular application. The one thing we did put in here is we do have a default for the variable frequency reference value on power up that we are moving in. They're a value of 32,000 by default. You could do something completely different in your application if you want. The last thing we will show you in regard to the I/O is the mapping that we have done here. So let's go to our global variable area here, and we have created 4 variables that are tied to the analog output, analog input, digital output, and digital input. We have frequency reference, our frequency feedback, our run signal, and our motor at rest feedback. And we put a HW on these to note the fact that these are hardwired. Before we exercise this, let's go in and take a look at our Modbus configuration. So back to the hardware configuration, Modbus RTU is a serial port protocol. So we go to the serial port configuration. MJ2 is our RS45 port. We have selected Modbus master here, and then we have our 3 levels of configuration. So we will quickly go through that. We left everything at defaults except we matched the serial parameters to the default of the drive. So these are the default drive's serial parameters. The other thing we have done is we have reduced our timeout to half a second because this drive is the only thing we have connected to our port. Same thing with acquired time. We have left pulling up the data as fast as possible, and we have taken advantage of the 4 double words of Modbus RTU master status to make sure we have plenty of good troubleshooting information. So here we go with our first level of configuration. On the device level of things, we have a single drive connected, which we have given a convenient name. It is Modbus address number 1. It uses PLC 5-digit addressing, and we took advantage of the additional 2 words of status that will tell us if there is a problem with any of the data that we have that we are trying to retrieve. And finally, we have our scan list. This is the data we are retrieving from the drive. Now in this case, we are using Modbus connection strictly for diagnostics. So we are doing read commands. If we were doing full control, we would have both read commands and write commands. So let's take a look at the data that we are looking at here. We have got 3 words of status information that we are reading into an array variable of a word type, just pulled read. So we are reading this data all the time. This is going to give us information including RPM and motor voltage and that sort of thing. The next thing we are going to be reading all the time is a single word that tells us the health of the drive. If there are a problem with the drive health-wise, we are going to know that right away because we are continuously pulling this data. And then we have a couple of other entries that are not continuously pulled but are only pulled when we need them. So we trigger them with another variable and ladder. So the first one that we are doing that with is the strip history. So if we have a trip, in other words, if that health bit we just looked at goes to 0, that means our drive is no longer healthy and we have got a trip condition. Let's trigger a read of the trip history. There is 10 consecutive Modbus words that can tend to contain the last 10 trip codes. So let's go ahead and read that information. And then the final bit of the data here that we are reading is similar trip times. So that is not the trip codes. Again triggered by turning on a bit in our program. Let's take a look at our ladder logic. We have already taken a look here at this default frequency value that we are going to make available here. Let's go to our Modbus RTU bit of code that we have got here. All we have done is we have broken out the 3 words of the data that we are retrieving from the drive that status information into individual variables, voltage, kilowatt, and RPM. And then we have got a trip that occurs. In other words, if we detect that our health word is no longer a 1, then we are going to turn on the one slot, the one shot, which is going to cause us to retrieve those 2 entries in our Modbus scan list. And then just like every Modbus example we do for Modbus RTU or Modbus TCP, we create a Modbus OK bit by determining that the number of good messages is incrementing, which means we are successfully talking to the drive. So this is the same logic we have used before. So that is what is going on the logic and configuration side. Now because this is a CPU250 and does not have a built-in screen, we are going to go ahead and use the data watch for our demonstration here. So the first 4 entries in our data watch are those analog output, digital output, analog input, and digital input that are wired to the drive, so we can see the status of those. And this is our 3 words of status information over Modbus that we are retrieving. So let's go ahead and turn on the drive and see what is going on here. So we have got a set for max frequency. Let's turn on the run bit and see what happens. As you can see, we are ramping up nicely there. And now we are at full speed, and while it is running, we do have the ability to change the speed. We are doing it from data watch. You would likely do it in a ladder logic, where you are manipulating the speed based on maybe some simple logic you are going to be doing in your logic. We are going in here from the data watch, and let's go ahead and move it back to full speed. And as we do that, you can see this diagnostic information we get. We have 230 volts, 5 kilovolts, and 1800 RPM. So that information is all happening here is a speed feedback, which is nearing 32,000 Hertz. So it is indicating a high speed here. It is at maximum, but remember we are dealing with analog here, so it is not going to be exact. We can stop the motor by turning off the run signal, and then our motor at rest bit that we are pointing at right now with our pointer just turned on. That means the motor just got to rest. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, hopefully that was beneficial to you all. As usual, the upcoming webinars will be under the support tab, so you can get them there at the links, and we'll be on again next Thursday at the usual time. So thank you all for joining, and we'll see you then.